rewrite what the situation was. So with last class, I said x prime is equal to ax. And I suppose that A has two real eigenvalues that are distinct, so such that lambda 1 does not equal lambda 2. And then I have three cases for this. So the first case was that lambda 1 is negative, but lambda 2 is positive. And we already saw that that means your equilibrium point is what? If this is the case, what do I classify the equilibrium point as? Static. Right. Now we'll try to do the other cases. So the other cases with lambda 1 and lambda 2 are both negative. And the third case is when they're both positive. So 0 is less than 1, and less than 1. So both positive. Okay, so let's do the second case. And of course, you don't need to use Mathematica. I'm quite confident Maple can do this too. I'm sure it can. You can? Have you tried it? Yeah. Is it as pretty as Mathematica? No. You can do that. You can do? You can do that. Yeah. I can change the colors too, but see now that becomes a nightmare in Mathematica to try to change things like colors and fonts. It's not nice. No. Okay, so example. So as somebody asked, I'm changing the schedule a little bit. Because this stuff is so new, I figured it would be better to do examples alongside the introduction of the new material. Instead of introducing it on Monday and Wednesday, letting it linger till Friday. So as you noticed, for every new concept, I'm trying to introduce an example as well. So hopefully it will be clear. Because it's better to, dynamical systems is best learned through example anyway, as you can see. So now consider once again, x prime is equal to ax. So once again, our linear system, where once again the coefficient matrix is just this diagonal matrix, lambda 1, 0, 0, lambda 2. But with this time, the difference is both lambda 1 and lambda 2 will be both negative. Lambda 1 less than lambda 2. Okay. And so you can imagine it's exactly the same case as before, but we have our theorem. So what is the solution of this system? From the first theorem I wrote down. So what are the eigenvalues of the system? And what are the eigenvectors of the system? For this simple diagonal matrix. Right, so therefore what is the solution? Yes, very good. So remember our theorem. No, I wrote, this is the first theorem I wrote down. No. Before I even began these great drawings. Yes. So remember, x of t is alpha, which is our constant, and e to the lambda 1t, b1, plus beta, e to the lambda 2t times b2. And of course, b1 is 1, 0, and b2 is 0, 1. Hopefully you remember. Now, notice something interesting. What is the sign of lambda 1 and lambda 2 again? So as t goes to infinity, what happens to both solutions? They both go. And once again, what is the equilibrium point of the system? The equilibrium. 0, 0. Remember, this is the most important question that you have to answer. What are the equilibrium points? Now, in this case, it's simple because you have a diagonal matrix. But in the future, it will be harder. So you have to get used to asking yourself every time, what are the fixed points, what are the equilibrium points? So the equilibrium point of this linear system is always 0, 0. So keep that in mind. And we wrote this out last night. But this is generally. So as you just said, so now the difference is all solutions tend to 0, 0, which is the equilibrium point, as t goes to infinity. All solutions. So if you let this system, supposing it represents some physical system, whatever, supposing that it run on for an infinite or a very long time, eventually all solutions to this system will approach the origin. Every one. So what we say is the origin, and you'll learn this term later, is an attractor for all solutions. It attracts every possible solution.
Black hole.
Actually, it's not to be that. But there's some differences. But, okay. So the question is, though, how do they approach the origin? For sure, as you can see, they certainly approach the origin, but do they do so in some chaotic fashion, or is it some clean-cut fashion? So let's see, how in fact do they go to the origin? Okay. So, let me consider, let's break up the matrix once again. Okay. So let me denote small x of t as the first solution, so lambda e lambda 1t. And let me denote by y of t the other solution. So beta e to the lambda 2t. Now let me compute the tangent vectors at each point. So in other words, let me compute dy by dx. And how in the world, if I have this, do I compute dy by dx? How do I do it?
Differentiate both with respect to t and lambda.
Chain rule, right? Oh, so dy by dx is dy by dt divided by dx. So what is dy by dt? Yes, very good. Lambda to e, lambda to beta e to the lambda to t. And what is dx by dt? Okay. So this simplifies, as you can verify, lambda 2 divided by lambda 1, beta over alpha times e to the lambda 2 minus lambda 1 over t. Okay, so what? What does this even mean? I've just done some calculations, but let's look at it a bit more carefully. So somebody brought this point up, I forget who it was last class, that I'm able to do all these fancy calculations because the systems are linear. But as you will see when we go to nonlinear systems, it's much more complicated. But it's also much nice because most physical systems are nonlinear. So these calculations are nice for now, they have their charm. But it will go away very quickly when you compare it to nonlinear systems. But anyways, so lambda 1 is less than lambda 2, both are negative. So in other words, I have it that lambda 2 minus lambda 1 is greater than 0. So lambda 2 is greater than lambda 1. What am I saying here about my slopes? What statement can I make? Very good. No. So it follows that because of this, it follows that these slopes, as it said, go to plus or minus infinity. Provided obviously that beta is not equal to 0. So, what does it mean for slopes to go to plus or minus infinity, then for the solution? Think about it. Oh, and what does that mean about the curve? The curve to itself. If you have an asymptote, how is it approaching? Think about it. What would those lines be for any solution? The tangent line. Yeah. So these solutions tend to the origin. So I'll just put 0, 0 because I don't want to write on origin. Tangentially to the y-axis. So in other words, you get something like this. And I'll draw it, well, I'll get the computer to draw it more nicely. But I'll do it rough drawing here. So once again, 0, 0 is our single and one origin point or equilibrium point. So all solutions approach this equilibrium point. So you get something like this. And you get the other.
So, for the force closing words, can that be like this?
Which one?
The last part.
No, we want, maybe I drew it badly, but we want every solution to approach 0, 0.
Yeah, but the slope is going to be really so it's like.
Yeah, let Mathematica draw it better than that. But in your head, you should see that each solution approaches 0, 0. I was nervous to do this unit because of the drawing that was required, but so we want both eigenvalues to be negative, so let's just, okay. So something like that. And you see in the middle there, along the xy axis, you have straight lines that go towards 4. So each solution curve is approaching the origin point, which is at the center of this curve. So I'll post these graphs actually on Moodle. Maybe it would be nicer for you to have reference. X-axis is
Up and down?
Up and down, yeah.
Okay.
Yeah. It's weird how I set it up, but you get the general idea. Okay. So then, if this is the case, that all solutions, so you can ignore my silly drawing and you focus on the actual one. Although this says something about my lack of artistic. Yeah, so that's a good point. So these are the integral curves, what we're interested in. If you were just interested in drawing the vectors itself, you can just do that. So you get the same. The arrows still go. Exactly. Okay. So you get an idea. So in other words, if this is the case, the origin point, so before, when you had one positive eigenvalue, one negative eigenvalue, we said the origin was established. Because some of the points attract, some of the points repel. But now the equilibrium point attracts. It does never repels. It attracts all possible solutions. So therefore, we call 0, 0 a Singh. That's the name. There are other words, so you may hear I think Boyce and Duprima use the word stable node instead of Singh. Some of the old Russian textbook use the word node instead of thing, but this is commonly in at least North American schools. It's called sink. Yeah. The idea is like think of it as, actually think of a physical sink, right? When water flows in it, it's all going towards the center. Right? So the center basin attracts the water flowing. So it's similar to it. So you have a saddle, now you have a sink. But notice here, what is the key difference between the saddle situation and the sink situation? Forgetting the drawings, what is the key difference? What is the one thing we changed that changed everything? The sign diagonal. Right. So the whole difference in behavior of the system depended on a slight change in the sign of the eigenvalue. So if you have one positive, one negative eigenvalue, you have a saddle. If you have both negative eigenvalues, you get a sink behavior. So this will play the most important when we go to non-linear systems later. Okay, so that's the first case we did a saddle. We've done the case where there's two negative eigenvalues. So what is the case of two positive eigenvalues? And you can imagine, actually, there's not a lot of work to do, because the case of two positive eigenvalues is just the opposite of this case. Okay. But let's write it down anyway. You don't want to write it down? There's a lot of two positive eigenvalues. So 0 is less than lambda 1 is less than lambda. That's a lambda 2, not some 0. So once again, your coefficient matrix is the same, but we would just change the signs of the other. So they're both positive. So in other words, you can think of the situation that our vector field is just a negative of the previous situation, right? So I'll put negative in quotation. It's just a negative of the previous example. Oh. Actually, in some ways, that analogy could work. Yeah. That's a good idea. So, in other words, in the sink situation, all solutions tend towards the origin as time goes to infinity. So what would it be in this case? They all move away. So in this case, so except now they all move away from the origin. So in other ways, I'll do my rough drawing, but then I'll show you the video. So if this is the origin, all solutions now move away from it. And this is the situation, then we call this equilibrium point a source. So we have a saddle, we have a sink, and now we have a source. So let me show you the case of this source. So both eigenvalues are positive in this case. So you see, they all move away from this. And the origin is that you can see it, it's in the center. The 0, 0. So you have exactly straight line solutions moving in one unique direction along the x and along the y.
This is just
Oh, it's very much related. Oh, yes. So, I've told you every possible case that can occur. So you can have two eigenvalues that are negative, two that are positive, one that is negative, one that is positive. What situation have I not covered? And assuming they're both real, what situation have I not covered?
very cool.
Okay, that I've not covered, but what other situation have I not told you? So that's one of them.
0.
0. Very good. So what happens when one of the eigenvalues goes to 0? Is it this board? No, it's that. I've lost track. I don't know. I'm all in the middle now. The computer has confused me. Because that's become like a fourth board now. So I go from 1, 2, 3, 4, and then I don't know why I'm saying this out loud. Anyway. So what happens when one of the eigenvalues goes to 0? So if one of the eigenvalues equals 0, then something very special happens. There is a straight line of equilibrium. In other words, in your coefficient matrix, if I set one of these equal to 0, you'll see you'll have an entire row of zeros, right? But I have two variables. So if I have one row of zeros, how many solutions do I have to the linear system? Infinite number. That's why. So if one of the eigenvalues goes to 0, one row gets missing from the coefficient matrix. Or in other words, one column as well, because it's a diagonal matrix. So if you have a 2 by 2 matrix or a 2 by 2 linear system, with one of the rows or columns completely missing, that means you have an infinite number of solutions, right? As you remember. But a lot of interesting dynamics happens, actually, when you have one zero eigenvalue. Okay, but the caveat is this. Even if you have one zero eigenvalue, the sign of the other non-zero eigenvalue still determines the behavior. So if the other eigenvalue which does not equal 0, then the sign of this eigenvalue determines the behavior of this. My chalk has become so small, it's become like that. Anyway, so let's see what this looks like. I won't attempt to do it. Why would I? So one of the eigenvalues is 0, and let me consider the first case where the other one is positive. You get something like this. So you can see in each case you have an infinite number of equilibrium. Let's change it. Let's make it negative. It's the other way around. But you have a line of equilibrium points, as you can see. So it's very different in the case. Very different. So it's just a trivial case. What happens if you go both? Then you get that. But that's not really true, actually. As you will see later. So, okay, so we have exhausted the case of real eigenvalues. We've done every possible case that can occur for the real eigenvalues. So, let us consider now what you want, the complex eigenvalue.
Sorry, just one quick question. Yes. Even though one of the eigenvalues is 0, the eigenvector being actually 0, has that any consequences?
Not necessarily. But you'll see this more pronounced in a non-linear case, actually. Linear systems is kind of, we're overdoing a little bit just to learn the concepts. But these concepts will really start to show their power when we study non-linear. So I ask you to trust me and be patient. Yeah. Okay, what did I just say? We want to do complex again, I'm the third one. I don't know why I'm losing track. So we've done all the possible cases of the real life. Clearly she is not impressed. Let me stop being distracted from my own comments. So once again, consider a linear system. But this time, consider the coefficient matrix not diagonal to be in a slightly different form. So this time, A will be in the form 0. I'll use beta for the constant instead of lambda just to keep it separate. Minus beta 0. So in this situation, our difference is that now the main diagonal is 0. The off diagonal elements now are not 0. So it's a non-diagonal matrix. Okay. And of course, I'm assuming that beta does not exist. Okay. So, what is the characteristic polynomial for my eigenvalue? Which is right. The characteristic polynomial. So recall we just solved for the determinant of A minus I lambda is equal to 0. In this case it's simple because the diagonal matrix is 0, so you just get a minus lambda here and a minus lambda there. So the characteristic polynomial, the determinant becomes lambda squared plus beta squared is equal to 0. So therefore, what are my solutions? Yes. Plus or minus I. So now I have complex eigenvalues. So just by changing the main diagonal to 0, I now get complex eigenvalues. Okay. So what are the eigenvectors is the question. Okay, it's the same practice as before. So the eigenvector, but as you notice, actually, we don't have to solve for both eigenvectors for the complex eigenvalue case. Why is that? If I know one, I automatically know the other, because they're conjugate. So the complex situation is nice on an exam, for example, because you don't have to do the other calculation. Alright. Because you see they're just complex conjugates of each other. So let's see. So complex conjugate means you just take I and make it minus I. Okay. So let's just compute the eigenvector for one of the eigenvalues. So I'll do it for lambda is equal to I times beta. So it's the same as before. We solve the same format of a linear system. In this situation, we'd like to solve minus I beta, beta, minus beta, and then minus beta, times xy is equal to 0. And as you can see, as usual, as you expect, one row is completely a multiple of the other. So we again have one equation with two. So once again, so we get that just looking at the first row, because you just have to look at one row. So you get minus I dx plus beta y is equal to 0. And of course, the solution to this equation, just by manipulating it, you get x is equal to minus I. So, your eigenvector then, your x is infinite, because y is just a parameter, it can be any real number. So your eigenvector then is xy is equal to minus iy. And I can of course factor out the y, minus I. And of course you just set y equal to 1 per convention. So this becomes minus I. So associated to lambda is minus IB, or IB, you get this eigenvector is minus IB. Actually, maybe in this situation, I wouldn't want to set y is equal to 1. And I'll tell you why. I can make it any number, but for this specific example, let me set it to something else. So, in general, I have y minus I1. Y can be any complex number, right? So let me just for, and you'll see the reason I'm doing this, let y equal to, let's just say I. So in other words, let me multiply this eigenvector by I. I can do that because it's so if I multiply this by I, what is the eigenvector? What's minus I times I? Is it minus 1 or 1?
1, because so that's negative.
I'm quite confident it's 1. But I squared is minus 1, minus 1. And what is I times 1? Okay, so therefore, the solution, or at least one of the solutions, is x of t is equal to e to the eigenvalue, which is I beta, times t, times the eigenvector, which is 1 I. And now it looks like completely I'm writing some font. The chalkboard font and that. That's what it is. I like it too, actually, but it's hard to do. Okay. But now, is this solution that I found real or complex? So it's a complex solution, but we started with a real system of equation. So remember we did in ODEs? It's not polite to give somebody a complex solution when they give you a real problem to solve, even though it's perfectly okay. But to see the pattern physically, what does this represent? Let's try to find real solutions corresponding to it. So it's the same trick as before. In other words, we want real solutions. So what do you think is the formula I will use? Yeah, the Euler formula. So recall that e to the I beta t is equal to cosine beta t plus I sine beta. Oh. So now, if I multiply e to the I beta t, it's just this number. So let me multiply this column vector by this formula. Because I'm multiplying it by e to the I beta t, e to the I beta t is this one. So let's do the multiplication of the matrices and see what we get.
So you're treating Euler as row vector?
Actually, it's a constant. It's one number.
Oh,
Because it's cos plus sine, it's one number. So in other words, like a constant, but not really a constant, but one element, I would say. So 1 by 1 matrix. Okay, so let me substitute this into that, or to that, and let's do the multiplication. Okay. So in other words, if I do that multiplication, what do I get? I get still a 2 by 1 matrix, because, as I said, it's a 1 by 1 times a 2 by 1. So if I do cos beta t plus I sine beta t times 1, I just get that number. And if I do cos beta t plus I sine beta t times I get I times I in here, which is minus sine beta t. And I get I times this, which is I cos beta. So in other words, I get minus sine beta t plus I cosine beta. Okay. But now, I wrote it like this because you can see, I can split this matrix into a sum of real and complex parts. I can always add matrices together if they're the same dimension. So let's do that splitting. So in other words, let me denote this splitting by x of t is equal to x. Let me put sub RE, means x real of t, plus x im, which means x imaginary. In other words, for x real of t, we get the following matrix cos beta t minus sine beta t. But the imaginary part, as you can see, is just sine beta t and cos beta t. And this is just so that. And this is just, of course, as you can see there, sine beta t cosine beta t. Interesting. So, indeed, as you saw previously, but it's the same idea, these individual solutions are also solutions to the system. Just like before when we found real and complex solutions, or the real and parts, the real part was the solution, the imaginary part was the solution. The real part and the imaginary parts are also solutions to my system of equations. Yes?
You just factored out the I. So.
Yeah, I didn't write it.
Okay.
Yeah. So really I should have written like so the real matrix and the imaginary part are also solutions. And we can prove that very easily. So if I take derivatives, oh, I'm out of time. I'm sorry, I didn't realize it. So if I take, I'll finish this. I lost track of it. I was having so much fun. I lost it. Okay. So there's no class next week, obviously. I will finish this on the Monday.